All right, so welcome everyone. Due to the late start, I will keep the comments brief. I promised to embarrass Tom, but now I'm off the hook, and he's off the hook as well. I'll just say that Tom came to us with wonderful recommendations from some small, backwoods Midwest school. But he proved his worth nonetheless. He'll tell you today about his work on phonon spectroscopy at LCLS, and hopefully he'll tell you what LCLS means so that I don't have to. But I will let you know that Tom, as far as I know, holds the records as the one student who has the most number of proposals make it through the LCLS committee, proposal review committee. Maybe I'm wrong. So anyhow, he'll tell us about a subset of those, and without further ado, Tom.
Okay, thanks for the introduction, David. Sorry for the delay, everyone, and thanks, Professor Demopoulos, for stepping in. So I think this title pretty accurately represents what I spent most of my PhD doing, so I'll try to translate it into English. So time domain spectroscopy means I was making movies in this context, so making measurements of things changing as a function of time. Phonons are a conceptual tool that we use to understand atomic motion, so I was making movies of atoms moving. And to do this, I was using a new tool called LCLS, which stands for Linux Coherent Light Source. This is an X-ray laser that's up the hill at SLAC National Accelerator Laboratory. And this is really the machine that makes all of the science you're going to see in this talk possible. It has short pulses, so comparable to the time scale at which atoms move. The wavelength is short also, similar to interatomic distances in solids. And it has high flux, which is necessary to see the weak signals I'm going to be showing you today. And I just need to say, as David mentioned, this is really an incredible machine, and what I'm going to show you is only a tiny sliver of the amazing science that's being done there. This thing beat all other previous X-ray sources by 9 orders of magnitude when it came online in terms of brightness, and it has really opened a new regime of X-ray science, and what you're going to see here today, I hope, qualifies as some of that. Okay, so the first question that might come to the mind of the US taxpayer is, why should I be paying you to use this rather expensive machine to look at atoms? And to answer this question, I'm first going to answer a different question, which is, did I make a better refrigerator? So if it were the case that over the course of my PhD, the US government paid me to engineer a refrigerator which kept your stuff just as cold while consuming less energy, it would save you money on your energy bill and better the lives of all Americans. And so it could be considered a good use of tax dollars. I didn't do that, though. But what would make a better refrigerator is if you had better insulation in the walls of the refrigerator. This stops heat from getting in and warming up your stuff, so the refrigerator doesn't have to work as hard. And so if over the course of my PhD I had engineered a material which had lower thermal conductivity at the same or lesser cost as the stuff they currently use in the walls of the refrigerator, someone else could use this to make a better refrigerator. But I didn't do that either. But atomic motion plays a big role in the thermal properties of materials, such as thermal conductivity. So maybe I use these measurements to come upon some new scientific understanding of what gives materials the thermal properties that they have. So then a material scientist could use this knowledge to engineer better refrigerator insulation, and someone else could use this to make a better refrigerator. Nope, I didn't do that either. So what I did do was try to understand how we can use LCLS to make fundamentally new measurements of atomic motion and access quantities that previously were experimentally inaccessible. And so at this point, it seems like I'm pretty far removed from the refrigerator, and it also seems like a lot of effort to go through for a refrigerator. But if you step back for a minute, I'm not just talking about refrigerators. This is the problem of heat, which comes up actually all the time. So you think of the complicated part of a nuclear power plant being the nuclear processes that power it, but actually most of the infrastructure and engineering that goes into such a facility is how to safely manage, transport, and extract useful energy from the heat. Your car radiator is a device that's designed to extract heat from your engine so it does not overheat. And in terms of our consumption of fossil fuels, if you look at the top energy-consuming appliances in the typical American household, most of them have to do with heat. So the first one is heating and air conditioning of your home. Ovens are another big one, and refrigerators. So heat is a big deal, and it has broad-reaching applications into many of the technological aspects of our lives. And so I hope that some of the techniques that I've been working on here will help us gain some new scientific understanding of heat so we can make some progress in addressing some of these very big problems. Okay, so now that I've told you how I did not make a better refrigerator, I'll explain what a phonon is. And then in the second part of the talk, I'll discuss this technique I use to measure phonons and how it works. And then I'll delve into some of the specifics that I worked on personally in my PhD, which is understanding how it is that we excite the phonons in this technique. And hopefully, if I have time at the end of the talk, to discuss how we can use this technique to really go beyond measuring phonon dispersions and access some fundamentally new information. Okay, so my go-to solid-state physics textbook is Ashcroft and Merman. So if you open this or a similar book and flip to the chapter on phonons, it'll talk about the harmonic approximation, which is the approximation that the interatomic forces between the ions are like perfect Hookean springs. If you adopt this approximation, write down some equations and do some linear algebra, you'll find that a convenient way to think about these is in terms of this system of coupled masses is in terms of its vibrational eigenmodes, a few of which I've illustrated here. So the spatial pattern by which these ions are displaced from their equilibrium positions follow plane waves, and so we can actually enumerate or label these different phonon modes by the wave vector associated with each of those plane waves, which I've drawn here as these arrows. And each one is an independent harmonic oscillator. So you can see that in each case, the ions are undergoing harmonic motion, and within the harmonic approximation, they are uncoupled from one another. So if we pick a particular direction of wave vector, typically for the acoustic phonons I'm showing here, higher wave vector phonons are higher frequency than lower wave vector phonons. So if we were to plot the phonon frequency as a function of the length of this arrow, we would get a phonon dispersion curve. So for the modes I was just showing you, they would follow something like this red curve, which has higher frequencies at higher wave vectors. And in the case where you have more than one atom per unit cell, you have additional branches which have non-zero frequency at zero wave vector. And I haven't illustrated those, and I'm not going to talk about them right now, but they will come up later. So we've had methods for measuring these sorts of curves for a number of decades now, and they give you a lot of information. They can tell you the speed of sound, it tells you a lot about the heat capacity of materials, and it also tells you something about the stiffness of the bonds, because the spring constants you use in that model affect the shape of this curve. However, if you continue reading in Ashcroft and Merman, a couple chapters later, the entire chapter is dedicated to all the problems with the harmonic approximation. So while this picture the approximation is pretty good, we don't want to abandon this picture completely. What it means is that these different modes are not completely independent of one another. There is some coupling between them. And this coupling plays a role in a number of important properties, one of which is thermal conductivity, so refrigerators. So we have ways of calculating how strong the coupling is between different phonon modes, but we actually don't have a method for measuring this quantity experimentally. And I've always found it kind of disappointing that there's an entire chapter in an introductory solid-state physics textbook dedicated to something that we don't know how to measure. So I may be being a little bit harsh. There are some things, of course, that these couplings are related to that we can measure. For instance, the lifetime of modes, or how long energy stays in a mode, is given by how quickly it leaves through each of these couplings. And so if you can calculate the rate of energy transfer for each coupling, it'll give you the lifetime of this mode. And so when we compare, the problem is when we compare this number the lifetime that we measure and this calculation, the calculation summed over all these couplings, and if the experiment and the calculation don't match up, it's difficult to diagnose where we went wrong. If we overestimated all of the couplings, or if we got some wrong and some right. And so I feel that if we could access this information experimentally, it could give us some insights. Okay, so the technique I'm going to talk about is what I'm going to I'll describe that now. So what we're going to do is we're going to take our crystal, shine X-rays on it, and we're going to rotate this crystal until we find a Bragg peak. And then we'll, in our beamline, install a line detector, which has the Bragg peak hitting in the middle at normal incidence. And so if we look at the line out from this line detector, we'll see that there's a Bragg peak hitting it in the middle. So no surprises yet. So now I want to ask, if I make a phonon mode displacement, what is how is this diffraction picture going to change? And it turns out that for this particular phonon, you will get side peaks next to the Bragg peak, which are associated with this phonon mode. So if you guessed that you would get these side peaks, you may have gotten a little bit lucky. I actually chose one of a very small subset of phonon wave vectors for which we can image these side peaks simultaneously with the Bragg peak. In particular, I chose a wave vector which is roughly parallel to the direction of the line detector. Now, I'm making a little bit of an approximation when I say that, but for our purposes, this is good enough. I don't want to get caught up in the details. So for instance, if I had chosen a phonon with this wave vector, you see we don't see the side peaks. Now, the side peaks associated with this displacement exist in some sense, but to find them, we'd have to rotate the crystal. And in doing so, we would fall off the Bragg peak. Okay, so going back to this one, now let's suppose I make the wave vector of this phonon mode displacement shorter. Let's see what happens. So these side peaks will get closer to the Bragg peak, and if I make it shorter yet, they'll get even closer. So what we can see is that this line detector is really imaging the reciprocal space of the crystal for us. And the Bragg peak is marking the position of zero wave vector. And what we're really doing is it's imaging for us a one-dimensional slice of the two-dimensional reciprocal space of this crystal. And what you're going to see later in the talk when we use a three-dimensional crystal and a two-dimensional detector is we'll be looking at a two-dimensional slice of the three-dimensional reciprocal space of that crystal. So basically, different points on the detector correspond to different phonon wave vectors. Okay, so now I want to ask, how will this diffraction pattern look different if we displace the ions in the same amount but in the opposite direction from their equilibrium? So let me show you that. So I'm going to bring them back to equilibrium and then displace them in the opposite direction. Okay, so it looks the same. So we can't actually tell if we've made this displacement in the positive or the negative sense. And the reason for that is actually the height of these peaks is proportional not to the phonon displacement, but the phonon displacement squared. A consequence of that is that if we now let these ions go and let this oscillate, the ions will be oscillating at the phonon frequency, but the peaks, these side peaks will be going at twice that frequency. So there's a factor of 2 discrepancy, and this will come up again. Okay, so again, higher wave vector phonons are typically higher frequency than lower wave vector phonons, so our acoustic phonon dispersion might look something like this. So on the next slide, I'm going to show you again this line detector. And I want you to imagine that we've used something, anything, I don't know, perhaps a short 800 nanometer pump pulse, for instance, to excite a whole continuum of phonon modes all at the same time in this crystal. So what you're seeing in this diffraction pattern is we still have the Bragg peak in the middle, and these wings represent a continuum of side peaks because we've displaced a continuum of phonon modes of many different wave vectors. And we want to know, now that the laser is gone, how is this picture going to evolve? So basically, the points out here at higher wave vector are going to oscillate fast. The points close to the Bragg peak are going to oscillate slow, and the frequency changes continuously in between. And it turns out that it actually looks something like this, which I wouldn't have guessed myself if you told me that. So there's no collective behavior here. It's not like the neighboring points are talking to each other in any way. It's just that each one is at a slightly different frequency from its neighbor. And so if you wait long enough, they will eventually dephase from one another. Okay, so the next picture is not a cartoon. This is real data, and you're going to see something that looks very much like this, but it's in 2 dimensions instead of in 1 dimension. So the points roughly here, here, and here are close to zero wave vector. The pulse arrives just about there. And what you can see is that the intensity, which I've marked as a color, which I've represented as a color scale here, in the regions near zone center oscillate slowly, while the regions further and further away oscillate more quickly. And so this generates a similar sort of pattern to what you saw on the last slide, where you get these fringes that start coarse and then become finer and finer and finer. But in this 2-dimensional image, they've actually formed these closed contours. So this is, to me, still kind of amazing. We're actually, in this movie, watching phonons oscillate. I mean, that's the power of this machine, LCLS. So I want to point out that what makes this possible is that the time difference between the different frames of these movies are 10 femtoseconds. So 1/100th of 1/1 trillionth of a second. Very impressive. Okay, so again, in this movie I was just showing you, if you pick individual pixels, so for instance this yellow pixel and then these darker and darker red pixels, you'll see that the intensity is oscillating like this, and the pixels closer to zone center, like this yellow one, are oscillating slower, whereas the higher and higher wave vector ones are oscillating faster. And so we're really seeing the phonon dispersion here. This data was taken, this data is germanium, the last slide was gallium arsenide. This data was taken by Deling Zhu, Mariano Trigo, and myself at XPP and LCLS. And the way we did it was we used a short 800 nanometer pump pulse to excite the phonons in the material, and then used the short LCLS probe to take a snapshot diffraction picture. And what we did is we set the time delay between these two pulses, and then collected, like, say, 1,000 shots, and then averaged those, and then that's one frame of the movie. And then we changed tau a little bit, collected another 1,000 shots, averaged, and then that's another frame in the movie. Okay, so if we want to know what is the frequency of these phonons, we can figure that out by taking a Fourier transform and just reading off what the peak is. But we don't have to do it just for these individual pixels, we can actually do it for the entire image. So what I'm going to do is I'm going to take the Fourier transform of every pixel in the image, and then I'm going to plot it in a movie, where this movie, instead of being steps in time, are actually going to be steps in frequency. So what you're seeing here is, if you can imagine, so for instance, the frame which is labeled 4 terahertz, whatever pixels you see lighting up, those pixels were, the intensity of those pixels is oscillating at 4 terahertz, meaning that those phonons have a frequency of 2 terahertz. Remember the factor of 2 discrepancy. And because these different pixels spatially mark different wave vectors, we're basically imaging with our very eyes right now the two-dimensional phonon dispersion surface over this two-dimensional region of the reciprocal space of the crystal. And so you can see that we start at low frequency, where we mostly see things lighting up near these zone center regions, and as we go to higher and higher frequency, pixels that are further and further away at higher and higher wave vectors light up. Okay, so another way you can think of this movie is over this 2D region we have a phonon dispersion surface, and in this movie it was sort of like I was taking this constant frequency frame and sliding it up, and the pixels we see lighting up are the pixels at the intersection of this surface, these two surfaces. So since we have basically the two-dimensional dispersion surface, we can of course get the one-dimensional dispersion curve by taking a line out across some pixels and plotting the Fourier transform of those pixels vertically on a color scale, and you get a picture that looks like this. And the dotted lines here are the calculated dispersion. This is for germanium. So this technique was originally developed by Mariano Trigo and my advisor David Rees, and considering it's still the early days of this technique and the early days of LCLS, I would say this is pretty impressive. So if you compare this to state-of-the-art inelastic X-ray or neutron scattering, we're already doing pretty good in comparison to the competition. So to get these sort of dispersions with those techniques, you would have to collect statistics for literally days on end. And that's what they do. They have dedicated beamlines to scan for days on end. We took this data over the course of about 2 hours. And what really makes that possible is that since we're not looking at the energy shift of the scattered particles, we can collect many wave vectors at the same time because we don't need analyzers, and we can use the full bandwidth of the LCLS. We get the frequency resolution from the time-resolved dynamics. And so let's talk about what the frequency resolution is. So I'm going to zoom in on one of these regions down here where there's clearly 2 phonon branches close to one another. And here I'm plotting the color line out of the black and red vertical lines. And so you can see that we're resolving peaks that are separated by something like half a millielectron volt. And this is already kind of state-of-the-art for inelastic X-ray traditional inelastic X-ray scattering. And here, there's a lot of things we can do to improve this resolution. So, in fact, as far as we can tell, the only fundamental limit to what energy or frequency resolution we can achieve is how long you scan the delay. Basically, how finely sampled your Fourier transform is given by how long you measured in time. So, I think the future for this technique is very bright, pun intended, because LCLS is bright. Okay. Bad joke. Okay, so coming back to this picture, I want to point out that we're seeing a pretty clear signal all the way to the zone edge here at the L point and the X point. And if you think about this spatially, zone edge phonons correspond to the shortest wavelength that makes sense in the crystal, which is like 2 neighboring unit cells are going in opposite directions. So want to think about, now I'm going to move on to the next part of the talk where I want to think about this in terms of the excitation mechanism. So here I've drawn what might be a typical phonon, which has a wavelength of, I don't know, maybe a few unit cells. And so on top of this, I'm going to plot, for sense of scale, what the electric field from our 800 nanometer pump pulse looks like. Okay, this isn't very informative, so I'm going to zoom out by a factor of 10. Okay, we're starting to see the curvature here, so I'm going to zoom out by another factor of 10. So now we can see at least one cycle of our 800 nanometer pump pulse, but this small subset of the crystal I was showing you is so small it doesn't even render on this page. So how can it make sense that a laser with an electric field of this scale can push two ions that are in like infinitesimally close on this scale in opposite directions? So I spent some of my PhD trying to resolve this conundrum, and basically there's a couple different ways that this could happen. One is if there's disorder in the crystal, and another is if we're actually changing the force constants between the ions. And it turns out in one case you expect the phonons to be prepared in a coherent state, whereas in this case you expect them to be prepared in a squeeze state, and I'm going to explain what I mean by that. And what we did was design an experiment that can tell the difference between these two, and it's going to show us that actually the right side of this picture is the correct one. Okay, so let's imagine we have some disorder in the crystal, some impurities or whatnot. In this case, you can imagine that these atoms interact with the laser light differently than do their blue neighbors. So if they absorb light more strongly, they might create some strain on a very localized scale. And then you can imagine that in this case, we're sort of pushing neighboring ions, separated by a unit cell or two in opposite directions. So this might actually allow us to couple this long wavelength light to these short wavelength phonons. And so to understand why I said I thought this would generate coherent phonon states, I want to think about one particular phonon mode, which is, again, just a harmonic oscillator, right? And here I've drawn the phase space for that phonon mode, where U is the phonon displacement and P is its conjugate momentum. So here with the crystal in equilibrium, we're starting at the origin in phase space, and if we make a phonon mode displacement, this corresponds to translating along the displacement, the U axis. Now, if we make this displacement and then we let this go, again, this is a harmonic oscillator. So this point in phase space, if I've chosen the scaling of the axes correctly, will just go in a circle like a normal classical oscillator. And so even though it's a strange looking oscillator because it's a collective mode, it's still an oscillator. It's just constantly exchanging energy between having the spring stretched and having the atoms having kinetic energy because they're moving. Okay, so in the case of disorder, I'm going to write down the Hamiltonian for this oscillator. I promise I'll keep the equations to a minimum. So this is just a free harmonic oscillator, and here this is our coupling to the laser light. So we said the laser would be able to push on this phonon with the presence of this disorder. And so we might expect that this force would have a temporal profile similar to that of the laser pulse. I'm going to take that laser pulse to be very short, so we're going to apply an impulsive force on this oscillator. And if you have a pendulum and you hit it with a hammer, apply an impulsive force, right after you hit it, it has not displaced, but it will soon because you've imparted some momentum onto it. And so the effect of this impulsive force is actually going to translate us up along the p-axis, at which point this will undergo harmonic motion. And so here we have what I'm calling a coherent phonon. Now, I want to remind you that what we measure in X-ray scattering is not the displacement, but rather the displacement squared. And so the thing we see on the detector is still oscillating at twice this frequency. Okay, so another way we could do this is that instead of pushing the ions, we're actually changing the force constants between them. So in this case, if we want to model this in our Hamiltonian, what I've done is I've added this perturbative term to the frequency part of the Hamiltonian, this omega squared part. And so you can see that if this is transient, has the temporal profile of the laser pulse, this is going to have the effect of transiently changing the phonon frequencies. And this is what you would kind of expect to happen if you change the spring constants for an oscillator. So to understand how this is going to work, let me just rearrange this a little bit. So I've pulled this interaction term from the laser out, and I've actually separated the two U's that were in that term. So if I were to cover up this part with my hand, which I realize I can't do now, but I was able to do when I practiced this at home. If I covered up this term and I said, the thing under my fingers is something that varies with time, you would say, well, this is a driven harmonic oscillator. You're multiplying something by U, so that's just a force. And in some sense that's correct, but actually in this case the force is proportional to the displacement. And so now I'm going to have us think about this oscillator, not as a single classical oscillator, as we did a moment ago, but rather you can think of it as a single harmonic oscillator or as a statistical distribution of classical oscillators. Either one is a fine way to think about it. But the point is you're not going to be occupying a single point in phase space, but rather some finite volume in phase space, which is why I've drawn this point as obnoxiously large. So now that we have this distribution, let's say, okay, now if we again take the laser pulse to be very short, what we're doing is implying an impulsive force which is positive on the right-hand side of this plot and negative on the left-hand side of this plot. And so what is going to happen is, something similar to before. We're going to translate up in P on the right, down in P on the left, and you're actually going to shear this initially isotropic distribution into something that has an elliptical shape. So if you now let this undergo harmonic motion, each point on this phase space will undergo the classical trajectory, and you'll get this sort of spinning helicopter type thing. So this is what I'm saying is a squeeze state. Now, unfortunately, for this thing as well, the expectation value of u squared, which is really what we're measuring, is oscillating at twice the phonon frequency. So just by looking at the time-resolved dynamics of the X-ray intensity, we can't tell the difference between these two. So we need to design an experiment that can tell the difference between these two. And this experiment is dead simple. You don't use one pump pulse, you use two pump pulses. So for a coherent oscillator, you sort of know that you want to, if you're going to apply impulsive force, you want those to be separated by half a period if you want the second one to stop the coherences generated by the first. Right? So the first one has the effect of, both pulses are going to have the same effect on the phase space distribution. So the first one pushes it up along the p-axis. So you want to wait for this thing to orbit all the way back down to the bottom, and then kick it again, and this will bring it right back to equilibrium. But in the case of the squeeze phonon, actually, this isn't what you want to do. So if you did this, actually, you would amplify the squeezing and make this ellipse have an even bigger, more messed up aspect ratio. So in fact, you want to wait a quarter of a period, because it's after a quarter of a period, it will have rotated 90 degrees, and if you apply the same shear you applied the first time, it will bring it back to an isotropic distribution. So I had the pleasure of doing this experiment with some colleagues at XPP at LCLS, and this is the result. So basically, this is the dispersion we got when we used only a single pump pulse, and this is what we got when using two pump pulses separated by 880 femtoseconds. Now, all the slides I was showing you previously were using a single oscillator, and so instead of changing the pump-pump delay, what we did is actually utilize the fact that in these measurements we're measuring a continuum of oscillators with a continuum of different frequencies. So for some of these oscillator frequencies, 880 femtoseconds will be 3/4 of a period, 5/4 of a period, or 7/4 of a period, which is what I'm labeling with these green lines. And what you can see is that these frequencies, the ones we expect to be stopped by the second pulse if we're actually getting squeezing, it does appear that the second pulse is stopping the oscillations because we see an obvious lack of signal at these frequencies. So, yeah, this indicates that the way we're coupling to these high wave vector phonons with the short wave vector light is actually by changing the interatomic force constants. And this is nice because it's kind of a general purpose thing, I mean, you can always expect that you'll be able to change the force constants. So there's a lot of reason to believe that we'll be able to use this technique on a vast array of different materials. Okay, so now that we've closed the lid on that one, I'm going to talk about this is the final and best part of my talk, which is how we can go beyond just measuring phonon dispersions and make some fundamentally new measurements. So up to now we've been using the laser to excite a whole bunch of modes, and for measuring the dispersion that's great because then you can read off the frequency of all these modes. But if you want to look at phonon-phonon coupling, this may not be the best way to do it. So in that case, what you might want to do is actually be selective about what phonons you excite. So if you can imagine exciting only a small subset of the phonons, say in one region of the detector, then what you might hope for is you strike it with a laser pulse, this small subset start oscillating like crazy, and then you can see that other modes on other parts of the detector that this thing you're excited are coupled to start to show some activity, not right when you hit it with the laser pulse, but after some time. as energy transfers from the modes that you excited to its target decay modes. And that's basically the experiment I'm going to show you. Okay, so how can we be selective about what modes we're exciting? We can actually, so it turns out that if a phonon has a wavelength that is similar to the wavelength of the light we're using to excite it, you can couple to it in a very direct sort of way. You can couple to it via first order Raman and IR processes. And so, but as I showed you in this cartoon earlier, the wave vector of our light is exceedingly small compared to the size of the brilliant zone, which is sort of the scale of this horizontal axis. So for all practical purposes, the phonons that have wavelengths similar to that of the light lie along this vertical line at k equals 0. And so the only ones that have any appreciable frequency are these optical phonon modes. And so this is indeed the case. You know, there are zone center optical modes which we can excite very strongly and somewhat selectively with our laser pulse. And so if we do so, we'll create a very non-equilibrium situation, and the material will relax by undergoing, having this phonon decay. And the primary process by which that decay happens is one where this high frequency phonon splits into two lower frequency phonons. And so if these two phonons that it decays into are degenerate, as I've sort of suggested in this picture here, then we need them to be half the frequency of the one that we originally excited at zone center to satisfy energy conservation. So basically, this mode is coupled, we expect to be coupled to these red modes. And you can see that they're at different wave vectors. So this is good. We have a chance to see that they're at different parts of the detector. So what we're going to hope is that we can excite this one at one part of the detector and see these oscillating at a different part of the detector. Now, recall this factor of 2 business. So these 1.4 terahertz phonons we're actually going to expect to see oscillating at 2.8 terahertz. But it turns out that actually the very center of the brilliant zone is right on top of the Bragg peak, and so this is a little bit special. So this mode we're actually going to expect to see at 1 times the frequency. So actually both of these we're going to expect to see at 2.8 terahertz. So the material we did this in was bismuth, which is actually famous for having a mode you can couple to very strongly with laser light. And basically what I'm showing here is this blue diamond. This region on the detector is close enough at least to brilliant zone center, so where this blue mode is. And then these closed red contours are places where we see oscillations at 2.8 terahertz and where we expect to have phonons that are frequency 1.4 terahertz, or at least we have good reason to expect that there will be phonons there. Now, one thing I should say is that in this image, when we looked for oscillations that were just above and just below 2.8 terahertz, there was nothing really going on. And so there was something very special happening at 2.8 terahertz in these regions of the detector. So let me show you what the time-resolved X-ray intensity looks like in these regions. So you can see that for this mode that we couple to directly, it responds very strongly right when we hit it with the laser pulse, so right at time 0, and we get these big, beautiful oscillations that have been very well studied in bismuth. But these red curves right at time 0 aren't doing anything particularly spectacular. It looks more or less like it does before 0, when nothing was happening. But if we wait some time, we actually see that oscillations begin. And by checking the Fourier transform, we can see that yes, in fact, the frequency of oscillation of all these things matches up right at 2.8 terahertz. And so, yeah, I mean, this is it. You're seeing it. Basically, this mode is transferring energy into these modes in a way such that they start oscillating. That the expectation value of u squared of those modes starts oscillating, so we can actually see it on the detector. And I mean, again, this is really the power of LCLS. Is if you want to see phonon-phonon coupling, I mean, this is it, right? Here's one phonon, here's another phonon. You put energy in this one and see it start making this one oscillate. So you're seeing with your very eyes exactly this process I was describing. So just to try to convince you further, this is those same curves where I've removed a moving average. And so you can see that the blue curve is oscillating at first very strongly right at time 0, and all it does is spend the rest of this time decaying. While the red trace isn't doing much at all at the beginning, and then oscillations start and sort of amplify up as it gains energy, or energy is being pumped into it from the blue mode. And you can also see that these two are right right about at pi over 2 out of phase, just as you would expect for a driven oscillator. I do believe this is the first time in momentum resolved measurement of phonon decay in bismuth or anything else. And I think with this we can now start to have a way to measure, what is the coupling between this blue mode and this red mode, for the first time. And I think that's really exciting, and I think it's probably my best work. Okay, so I'm the one up here getting all the attention and accolades, but I had a lot of help. First and foremost, I want to acknowledge the people who actually sacrificed sleep and elbow grease to get this data. So the other members of our group who helped with beam times, especially Mike and Mason, whom with I shared many beam time experiences, both good and bad. Mariano and David, who came up with all the good ideas you saw in this talk. The beamline staff at XPP for supporting an instrument that made these measurements possible, and especially DeLing, who really took a special interest in this technique and to understand it and what our instrumentation needs were. We had theory support from the other side of the world. Of course, I need to thank the people who direct tax dollars my way, so the Office of Basic Energy Science in the Department of Energy. And then, again, this is a big day for me, so I also wanted to thank some people on a more personal level. So I had a lot of great friends in my academic career. So I had great friends at Ohio State, people, especially the guys I lived with in the Netherlands, who helped me navigate the land of the Dutch. And at Stanford, I've had a lot of really positive, supportive friends, and I'm really thankful for that. I mean, just how many good friends I have in this room, I think, is a testament to that. I had great teachers growing up, particularly I had a high school physics teacher who I think, as much as anyone, propelled me to where I am today. And I had great mentors. So Augustine Urbis at Wright-Patterson Air Force Base had a PhD in physics from MIT, and I think he was the one who first planted in my mind the idea that a mere mortal could get a PhD in physics. Professor Suri at Ohio State really had, made me believe in my abilities and gave me the confidence to get to where I am now. Ewan Blomink at Delft. And then here at Stanford, of course. So when I first joined David's group, I was cocky and thought I could do any experimental technique, but I simply couldn't have been more wrong. This stuff is totally impossible. So thankfully Mariano was there to show me the ropes. And especially at the beginning, but really throughout my whole PhD, he's been a mentor and someone I could turn to for not just advice on the big stuff, but also some of the nuts and bolts. And then, of course, David. So when I first started my PhD, when I was looking for an advisor, I was pretty open to what kind of science I wanted to do, but I really wanted to find an advisor I felt like I could get along with. And I think a lot of people thought that was kind of weird, but I don't regret it at all, because grad school can be a real pain, even when your advisor is not a jerk, I can tell you. So, in addition to being very bright and coming up with lots of great ideas and cool projects to work on, David has been honest, and I always felt like he has had my best interest in mind, and so he deserves a lot of credit for this as well. Oh, and of course, the mentors I had for the first 18 years of my life. So my grandma Connie always made me do my homework before I could go out and play with the other kids, which is a philosophy I did not agree with at the time, but it turned out to be a good investment. And last but not least, my parents, Tom and Gail, who went out of their way to give me every opportunity to succeed in life, and I will always owe them for that. Okay, that's it. Thanks.